Knowing how much power your vehicle makes is probably one of the most important things if you're doing any sort of development, testing, tuning. Dynos are great for relative power numbers, and they're a great tool for knowing if you put a new part in your car or truck or UTV or whatever, and you want to know what adjustment it made. But you have to be really smart about how you set up the dyno and how you run the test. And generally, it's only good for a pull and gives you a peak power number or relative power. If you want to measure torque on a vehicle on the road, really the best way to do it is the way that all the major automotive manufacturers and power sports manufacturers do it, and they use things called strain gauges. Strain gauges are a sensor that you can glue to the shaft. Designers and engineers use them all the time to measure deformation of a part. So you take this little sensor and there's a very scientific process where you adhere it to your surface. It could be plastic, aluminum, steel, carbon, fiber. It can be any material. In this case, we're going to be using strain gauges to measure the torque and horsepower on our 2022 Ram 2500 with the 6.7 diesel. This way, we can see what it takes to tow a trailer. We can see what kind of power it puts down if you tune it or if you have different tires. Today, we're just going to do a highway pull from 0 to 75 on an on-ramp. But it really gives you an idea of the baseline of this truck. We're measuring data super fast. So we're measuring at about 2,000 hertz. So that means every second we're taking 2,000 points of data. If you're measuring data off of the can, or you're plugged into the OBD, you're looking at 20 to 50 hertz. And this is really important if you're trying to measure transient events like wheel slip, clutch slip, that kind of thing. We'll walk you through the process today that we go through to turn this into a live dyno. We can gather data anywhere, anytime. So the first thing we need to do is we need to determine where we're going to grab the power from. In this case, we're going to be using the main drive shaft that goes from the back of the transfer case to the rear end. That's the standard baseline. That's what most of the driving is. If you wanted, you could put one on the front drive shaft or all 4 drive shafts, well, all 6. We could do 6-wheel drive, we can do boats, UTVs. We can really do anything. We even did a test for a customer on a garage door. Anything that spins or bends, we can measure the torque on that. So once we've decided that we're going to use that shaft, the next step is we got to mount the strain gauge. The system we're using has to cure for 24 hours. Then we cover it with the gauge protection material, and then we print a little housing to cover the whole thing and include the telemetry. In this case, we're going to be using a radio frequency telemetry system that we'll use to pull the data from the strain gauge and send it to the computer in the truck. Once we have that, then we have to make the fixtures that we use to mount the drive shaft into our static torque test machine. We try to manufacture as many parts of the fixturing that we need for testing in-house as we can. It helps us keep costs down and improve lead times. The back end of this drive shaft is pretty straightforward. It's just 4 bolts, so we just drill and tap some holes in a plate. The front end is a little bit more complicated because it's a female spline. We start with a 2-inch block and bore a hole in it. And rather than make the spline that goes into the female spline of the drive shaft, we opted to just buy a transfer case shaft and cut the end off. This gives us an opportunity to show a different piece of equipment that we have. It's our axial press that's instrumented for force and displacement, so we can measure force and movement as the part's being pressed. This is useful if you're trying to design a part like a spring, or if you want to measure how much of an interference fit you have on a part. This is the block that we just machined, and then this is the spline shaft that we cut the end off of. Then this is the force load cell that reads in pounds here, and then this is force over time, so you can see we hit a max of about 2,500 pounds, so it's a pretty tight fit. And then right here, we actually have a displacement measurement, so we can measure within 3 decimal places how much the system moves. Once it starts going, you'll see it, all the different pieces of the test. When we do force over time like this, it really helps paint a better picture of what's happening throughout the test. You can see what the part does in real life. So once you have the fixture pressed together, the next step is welding. And then after that, we go over to the static torque test machine. This is the backbone of all of the torsional testing that we do. It has an 8,300 foot-pound load cell that is calibrated by an outside house. And then we also have an angle finder back here that allows us to measure stress strain on a part. We can break it if it's under 8,300 foot-pounds. In this clip, we're going to be using it to calibrate the telemetry. So that's underneath this printed housing right here, and that's the red number. And then the load cell, the torque cell, is here, and that's the green number. So this type of fully reverse torsional loading is pretty common in fatigue testing and calibration of parts. It gives you an idea of what everything is doing when you go from one end of the full scale all the way to the other. The last step in the process is heading out to the field to gather data. We're going to be doing something pretty simple, just a highway pull onto an on-ramp. This is the number that we're looking for. So this is the number that comes from the calibration that we just did. This is the driveshaft RPM calculated off of the wheel speed. We're working on a design to measure the driveshaft speed, but for now we're just going to calculate it off the wheel speed. And from there, we can calculate the horsepower of the driveshaft to see how dynamic a simple event like pulling onto the freeway can be. When I started this run, there was a little wheel slip, so we'll see that when we look at the data after this pull. So we're just going to watch the pull straight through, and then we'll go look at the actual data. Oops. Here we go. So this looks like a lot, but when you're able to zoom in on each little section, it gets a lot easier to digest. This is a graphical representation of the data display from the video. So all these are the same numbers that you saw, plus a couple temperature and pressure things. Because we are recording so fast, we can really see some interesting nuances in the data. So we'll walk you through the colors. The red is the driveshaft torque. That's what we calibrated. This is that calibrated horsepower. Engine RPM, driveshaft RPM that we're calculating off the wheel speed. This is the throttle position. This is the calculated load. So this is the engine trying to decide based on some parameters, fuel pressure, usage, engine speed, gear, all that stuff. It knows roughly how much power is being used. And then this is the miles per hour and the mass flow rate of the air. And all of the colors in the graph correspond to the colors over here. The numbers on the side are average numbers. We use this as a live display, and if you show the actual numbers here, they move around too fast to read. So there may be a little bit of difference between the number that you see on the left side and the value on the graph. The whole thing is about 10 seconds. Now, keep in mind, the red line and this green line are the only lines that are not on the can, meaning they're the only ones that are synchronous. Those are the only data channels that are being recorded at 2000 hertz. All of the rest of them, you'll see there's a point here, point here, point here. CAN data is asynchronous, meaning that it comes digitally off the bus when it's prioritized in the system. So these data points are not particularly reliable when you start zooming in this far. These are really good for a relative number, but these data points are, this is real. This is what is happening. So we can do some assumptions, and we'll walk through each part of the data. So first thing right here, this is, the yellow line is throttle position. So this is what the computer thinks the throttle is. Now from this point to this point is half of a second, roughly, to go from 0 to full throttle. And now you can see the torque start to build, and it all kind of makes sense. The horsepower is starting to build. So you can see as when we hit the throttle, the engine speed starts picking up. A quarter of a second later, give or take, again, it's asynchronous. And then the torque starts coming on. Let's zoom in on the wheel slip from the start of the run. This is what spinning your tires does to your drive shaft. You get a torque oscillation of almost 800 foot-pounds here. And, that's how things break. The peak torque that we saw was 1,830 foot-pounds.
Now, until we get the system on that can measure drive shaft speed, the horsepower number is relative again because it's based off of the can, but we can still get a good idea of trending. And you can see that the horsepower goes up and the torque goes down because that's how the horsepower equation works once you've reached full engine power. One of the other cool things that we get to see when we start looking at the data on a highway pole that you don't get to see on a dyno, when we zoom in on the shift points, you can actually see the torque dips before the gear shift. So this line here is the gear shift. So this is second, third, fourth. And you can see we're continuing to build speed. Then when the power drops, the rate of change in speed drops. Now we're approaching our peak horsepower. And this makes sense because as we move across this graph, we're at max engine load here. And then once you've reached the max output, now in the horsepower equation, your torque starts dropping because your speed, you can't produce more torque to keep up with the speed. So now we're at almost 70 miles an hour. Here is our peak horsepower number. We saw max horsepower of about 346 horsepower, 727 foot-pounds. But the torque is low because the speed is up. So now we're at 75 miles an hour. Your torque drops significantly. We're down to 2% throttle and we're maintaining speed. Hopefully that sheds some light on how we do what we do and why we do it. If you like this video, share it with a friend. If you want to see us break the drive shaft that came with the truck, click the link. Otherwise, all the important social medias and website links are in the description. Thanks for watching.